support reactions acting on either side of the section. Bending moment equal to the algebraic sum of the moments above the section of all the external loads and support reaction acting on either side of the section. How to find a bending moment? Now recall the bending moment equals to the force into perpendicular distance. Now comes the application and uses of shear forces. You can go through this, where the shear force and bending moment diagram are useful and how to find it. Now comes sign convention for shear force. The difference between shear force and force. Force is normal force acting on a system. Shear force usually acts along the surface or tangential to the surface. Now in general force convention, we use the upward direction load or reaction we take as positive, and downward direction we take as negative. But in case of shear force diagram or shear force, there will be a little different. This is a cantilever beam and load is acting vertically downwards with a W. The shear force we are going to find for the entire surface of the beam. Now either you can start from the left or the right, but the thing is, if you're going to start from the left, the convention is different. If you're going to start from the right, the convention will be different. So today I'm going to show you tricks to remember. Remember the word run. R-U-N. So what is this run means? R stands for right, U stands for upper, and N stands for negative. Right side upward direction, right side upward direction will be negative, or we can say it's a vice versa. Right side downwards will be positive. So you can either remember as or DP or run. Two things to remember relevant to the right side. If you feel it is unnecessary, so you can just omit it, let it go. Just remember only thing called run. So first remember the sign convention. Later I will come or explain how to solve the shear force. Next comes sign convention for bending moment diagram. So in bending moment diagram, either it can be a positive or negative. But in bending moment we use two technical terms. One is a sagging, another is a hogging. If the bending moment is positive, we call as sagging, and the bending moment is negative, we call as hogging. But easy tricks how you can remember those terminology. What is this? This is a smiley. So if you keep two dots on this beam, it creates a smiley symbol. So smile S, smile and sagging. That means when you smile, you give a positive effect to the people. So positive. Bending moment diagram. If you remember one and another one, will be obviously the opposite one, and or we can say heartbroken. You can remember heartbroken for hogging. So hate and hate. So positive, when you smile, you give a positive effect, that is a bending moment diagram. Sagging, S sagging, and the other one is a negative bending moment we call as hogging. That's how I think it will be very easy for you guys to remember this sagging and hogging. Next, I will tell you few important points. Like if you draw the area of a shear force diagram between the 2 points, what it explains that if you do a calculus is a bending moment diagram. Next comes the slope of a bending moment diagram is a shear force. This can be a 1-mark question in your MCQ. And shear force can be explained as a dm by dx. Actually, d by dx is called as slope with respect to the span length. Next comes, if the shear force is 0, what happens? That slope of a bending moment diagram is 0. That what happens, that means the bending moment is constant. So you know very differentiation very well. If you differentiate any constant terms, what you get 0. So obviously the bending moment will be constant, so only it's getting 0. Now when the shear force is 0 or the slope of a bending moment is 0, at that point what happens, either the bending moment is maximum or minimum. These are the technical or these are the tricks or tips to remember, or you can cross check this thing. This is a formula how the load with respect to shear force and the bending moment. Cantilever beam with point load. Now this point load is acting on a free end. Now how you're gonna do it? First you have to find the reaction force. So if the load is acting here, from here another reaction force will be taking place. So consider R. R is a reaction force and load here. So what if you do an equation, that is summation of vertical force, what you will get? You will get the same thing, that is R will be equals to W, because no other horizontal force is acting, so you can ignore it. So this reaction is R is also the equals to W. Now you start from here. What I have said, run, R-U-N, run. So what is that run? That is right side upper will be negative, or right, that means right side, this is downward direction, so right side downward will be positive. Now take a this is a imaginary line, or this is a surface line. From here what you're gonna do is you're gonna take that same magnitude upward direction, that is of W, and you get as a rectangular bar. Okay, this is how you draw the shear force diagram. And when you draw the shear force diagram, the shear force for a point load we get as rectangle, and for a bending moment you get as an inclined line or a linear path. Next comes cantilever with UDL. Here is called as UDL, that is uniformly distributed load. Now in case of UDL, the unit is Newton per meter. Make sure in UDL we can write as small w, not capital W. Small w can be converted in capital W when we multiply with the entire span length. See here, W equals to small w into L, we get as capital W. Got it? Now shear force diagram. Shear force diagram, here what happens? It is an inclined line or linear path for cantilever with UDL. Now if UDL you need to find for a moment or bending moment, remember for UDL, especially for UDL, you have to use this formula, small w into length, that is span length, into half of the span length. That's how you can find the UDL for moment for the UDL, and you get as this WL square minus 2 by 2. And once you get any square terms, that nature of a curve gives a parabolic in nature or parabolic curve. Next comes similarly like as a cantilever with a gradually varying load. GVL means gradually varying load. It's gradually varying. So in case of gradually varying, for the shear force you get as parabolic curve, and for the bending moment you get as cubic curve. Now I will sum up this thing, shear force and bending moment. The shear force considers 1 degree and the bending moment is a 2 degree. Why I have written is, see here we have W. When we are finding for bending moment, we have 1 degree has increased, that is L. Now comes here we have small WL. Here 1 degree has increased, 1 more L has been added up. Here similarly, it's very easy way to remember this. So here first comes rectangular, then inclined line, crossway it comes inclined line, or we can say linear path. Then again in crossway it's coming parabolic curve. Here also parabolic curve, and the last one is a cubic curve. And the same thing follows with a simple supported beam. The pointed load in the middle. Now first, to find this shear force, you have to find the reaction force first. After finding the reaction force on both the ends, what you're gonna do, you're gonna find out this is this is L by 2, here also L by 2. The total length is L, this is L by 2. Now from here also you can similar way you can find that. So here also it's forming two rectangular. Here it's inclined, here also inclined. You have to remember this diagram, and this is a parabola. When there is a nature of parabola, there will be some curve. Here for gradually varying load. Here also parabola, here also this. Now remember this thing. For this also same thing, rectangular, inclined line, parabola, parabola, cubic. So I guess this is a very with that shear force has been given here. You have to remember this formula. Shear force has been here. You have to remember this formula. It's better you remember this chart with the nature, and these are the bending moments here. This is also can be written linear. This one in a beam, and it get deflected from its original position. That is meant by deflection. The slope is the angle between the initial position before the load is applied and the deflection position after the load is applied. It's a very simple concept. Now in this tutorial I will tell you how you can memorize the deflection and slope along with the shear force and bending moment formula. Today I am gonna tell you about two beam. That is, first category is a cantilever beam with point load. Second one is a cantilever beam with UDL load, uniformly distributed load. And the third one is SSB, simple supported beam with a point load at the center. And the fourth one is simple supported beam with a UDL load. Now these are the commonly they ask. If you know this thing, you can attend any question. Now here the first column we have shear force. Unit is Newton, or it can be written as kilonewton. The second one is bending moment, Newton meter or kilonewton meter. Now third one, slope denoted by theta, and deflection is denoted by the letter del. In some book you can find they are also denoting the deflection in terms of y. Now you remember this chart. What are the categories? 4 categories we are explaining here. These are the 4 common categories. First, we are considering the shear force as 1 degree, then second, third and fourth. Now, already in my previous tutorial I have said about this shear force and bending moment. Now in this I will also add the slope and deflection. So how you can remember these terms? How you can remember this formula, this coefficient? You know the slope means WL square by EI. This is a common thing. But how you can remember where to keep 2, where 3, where 6, 8, 16, 48, 24, 3, 8, 4, 5, 3, 8, 4. So I will show you today, I will show you a very easy trick you can remember this thing. Now let's see this thing. What I have done here? Here I have written only the coefficient thing. What is the common thing? W. Bending moment we have, what is a common thing? WL. 1 degree increasing, that is L is increasing. Here slope we have WL square. Here we have L, here we have L square by EI. Okay, what is E? E is a Young's modulus, I is a moment of inertia. Now in deflection here we have what? L square. So another 1 more degree will be increased. So WL cube by EI. So these, you remember this thing, WL square by EI, and for deflection WL cube by EI. Now we have this 4 sets of, here we are going to see basic or common 4 sets of beam. Cantilever with point load, UDL, simple supported with point load, and UDL. These are mostly commonly asked. If you know this thing, you can attend any of it. Now you see, either you can split this 2 part, shear force bending moment one side and the slope and deflection one side, or if you feel it's difficult, you can ignore it, just let it go. Now second thing, if you see the column, it is forming a triangle. Okay, see the cross rows, it's forming like this. Now if you look carefully, this first one we have a triangle, and the second, third, fourth and fifth and the sixth one having a circle or oval. And okay, for your understanding, let the last one, let it go. Now you see here we have 1 1 1. The next one, here also we have 1. So if you divide by 2, you get 1 by 2. Here also 1 by 2. Now from here, bring this middle term here. Here we have 1 by 2, and when you divide this 1 by 2 again with divided by 2, you get 1 by 4. See that last one, here we have 1 by 3. When you divide this term with 2, you get 1 by 6. Now you divide whatever in this term, you divide by 2 again, you get 1 by 8. Now this 1 by 8 divided by 2, you get 1 by 6. And this, you remember, this both the ends will be same. Now next you divide this term with divided by 3. So what you get? 1 by 2 4. Now this term again you divide by 2, you get 1 by 4 8. And the last one, there is one more way you can remember, that is Z technique. What is Z technique? You can see what the first one, we have a triangle. From the triangle, if you divide it by 2, you get 1 by 2. Then next, when you again divide it by 2, what you get? 1 by 4. Then again you further divided by 2, you get 1 by 8. Now at this junction, you can either go this way or like this way. Now in this junction, what you do is, the first one you divided by 2, and the third one means and the second one you divided by 3. So if you divided by 2, you get 1 by 16, and if you divided by 3, you get 1 by 24. Now again, if you further divided by 2, what you get? 1 by 48. And the remaining you already have been known that what are the figures will come there, and the last one I will come at the end. Now see here, let's focus on the slope and deflection. See first coefficients 1, 3, 6, 8, 16, 48, 24. Now how you can remember? Another way to remember, first you from 2 you multiply 3 from here, what you get? 6. Then next, you from 2 you multiply 4, what you get? 8. Next, from 8 you multiply 2 again, what you get? 16. Now from 8, if you multiply 3, what you get? 24. Now next, from 2 and 3, what comes? 6. So from 8 again you multiply 6, what you get? 48. Now the last term, how you can remember? You might have a confusion, that is 5 by 384. What is that? 348 or 384? What is it? Like you might get confusion about this letters. 5 by something was there, so you might get confusion. So I will tell you, see here, if you remember the series 3 8 4, you see here it forming 384. So you just write 5 by 384 to avoid your confusion. Next comes fixed beam with point load and fixed beam with UDL load. Here I will show you deflection, beam and deflection. So here you have to remember what is a beam formula for point load and the beam bending moment formula for UDL load. And the main criteria of this thing is like how this and simple supported beam are interrelated. So you see the formula, deflection formula WL cube by 192 EI, and for UDL load that is small w L power 4 by 384 EI or WL cube by 384 EI. Now how these two are related? These two are related comparison with a simple deflection of a simple supported beam. For point load it is 0.25 of deflection of simple supported beam, and in case of fixed beam of VDL load is equal to 0.2 of deflection. From that particular element I am focusing on a small precise element. On that element it undergoing some force. See, as it given in the figure, along the x-axis the tensile force is taking place, and along the y-axis a compressive force is taking place, or we can say compressive stress is taking place, and along the surface and shear stress is undergoing. So for this particular surface we can say if we have a shear stress is 0 for a particular plane, then the plane of the shear stress or normal stress can be maximum or a minimum, that is known as a principal plane. It can be sigma 1 and or sigma 2. Mostly the sigma 1 is denoted as a maximum principal stress and sigma 2 is denoted as a minimum principal stress, and the formula is displayed in your screen, equals to sigma x plus sigma y by 2 plus or minus root over sigma x minus sigma y by 2 whole square plus tau xy whole square. When we are considering a maximum, we will consider here as a positive, and when we are considering a minimum value, we will consider as a negative. Okay, so tau max, that is maximum shear stress, equals to plus and minus root over sigma x minus sigma y by 2 whole square plus tau xy whole square. In case of maximum shear stress, the tau xy will be 0, so you will get as sigma x minus sigma y by 2. And this is a formula, that is angle, which angle plane of axis it is creating a maximum shear stress. Then the purpose of Mohr circle, it is actually for a visual tool used to determine the stress at a given point in a relation to the angle of orientation of the stress element. As you can understand, there are 4 possible variations in Mohr circle depending on the positive directions are defined. So here comes, it can be a sigma 1, sigma 2 or sigma 1 or sigma 3. You can name anything, sigma 2 or sigma 3 plane, where the normal stress and the shear stress will act. So sigma s is also can be written as tau s or tau xy. So this explains that always the sigma 1 will be greater than sigma 2. And if you're dealing with the sigma 2 and sigma 3 plane, that means that there is two principal stresses would be sigma 2 and sigma 3. Now let's see the normal stress. This is a formula for normal stress. Sigma n equals to sigma 1 plus sigma 2 by 2 plus sigma 1 minus sigma 2 by 2 cos 2 theta. Now we can also write as capital C plus R cos omega. This omega is nothing but the 2 theta value. We are simplifying this above equation. What is C? C is the center of a Mohr circle and R is the radius of a Mohr circle. So what is C then? Here sigma 1 plus sigma 2 by 2 and R sigma 1 minus sigma 2 by 2, as it has been written over here. Now considering the when at what condition we will get a maximum and minimum normal stress. Now consider the theta value is 0. Now if you apply the theta value 0 over here, so what is cos 2 theta? We'll get as 1. Now applying that here, we will get as sigma n equals to sigma 1 plus sigma 2 by 2 plus sigma 1 minus 1, sigma 1 minus sigma 2 by 2. If you simplify this equation, we get a sigma n equals to sigma 1. That is a maximum value. Sigma 1 is a maximum value. Now consider the theta value is 90. Substitute in the same formula, that is a general equation formula. We get as cos 2 theta equals to minus 1. Then if you substitute that here, we get as this equation simplify and we get as theta n sigma n equals to sigma 2, that is a minimum value. So from the above we can generalize that sigma n equals to sigma 1 at sigma equals to theta, that is a maximum value, and theta when theta value is 90 we get as minimum value. Apart from that, there is some sign convention, that is when we get as normal stress is positive, that means the nature of a stress is compressive. When we get a negative value, we get, that means that having a nature of a tensile. That means when the sigma n is less than 0, when the sigma n is less than 0, it's a tensile, and when the sigma n, that is normal stress, is greater than 0, we get as a compressive strain. Then comes shear stress. Shear stress formula is sigma 1 minus sigma 2 by 2 sine 2 theta. Now similarly we have studied the radius formula, that is sigma 1 minus sigma 2 by 2 is a radius, so we have written here that is tau s or sigma s, both are same, equals to r sine omega. So what it represents, that here when is the minimum condition, when is the maximum condition. Mostly in competitive exam they ask this kind of question. So in shear stress, minimum will be when theta is 0, 90 degree or 180 degree, and maximum when the theta is plus or minus 45 degree or sigma 1 minus sigma 2 by 2. And from here if you need to find the diameter, that is 2r, so we can write that differential stress, that is diameter of a Mohr circle is sigma 1 minus sigma 2. This is a general formula when we are considering the tau xy is not equal to 0. So how we can remember this? See the formula, tau equals to sigma x minus sigma y by 2 sine 2 theta plus tau xy cos 2 theta. Now what is sigma n? Normal stress, minus sigma x plus sigma y by 2 equals to sigma x minus sigma y by 2 cos 2 theta minus tau xy sine 2 theta. Now here you see these are the common terms in both the shear stress and normal stress, but see their sine and cosine terms are getting exchanged. See here we have cos 2 theta, here the tau xy have a cos 2 theta, here we have a minus, here we have plus, and tau xy sine 2 theta, and here we have this value into sine 2 theta. This is a Mohr circle. This is how you have to draw the Mohr circle. Now comes some special states of stresses. There are around 4 important stresses, that is uniaxial, biaxial, pure stress, axial stress, and triaxial stress. So I will focus a generalized way with a Mohr circle, how they are denoted. What is meant by uniaxial stress? It can be having both the sigma 1 or sigma 2. If you're considering a 2D plane, So one of the axis will be non-zero and another one will be equal to 0. If you are considering a 3D plane or a 3D axis, then definitely one of the axis should not be 0 and other two should be 0. As you can see in the figure, that is having some value, positive or negative, it can be anything. So if it is having a positive value, that means it will give an positive impact. This is a positive quadrant and this is a negative quadrant. And similarly, if you want to find for the uniaxial tensile stress, you will have a negative here. So this is a summary of uniaxial tension and uniaxial compression stress. Next comes biaxial tension. Here one principal stress equals to 0 and other do not, that is the sigma 1 or sigma 3 has to be 0 and other two may be positive or negative. As you can see that one of the thing has to be, among the three, one of the thing has to be 0. So this one is both the sigma 1 or 2 or whatever you consider are in tension. This is in compression, and here one of the thing, this side means tension and other side is a compression. Here comes axial stress. In axial stress, it expresses that if among the three axes, the any two will be equal to each other and another will be non-equal to another. That means it is an axial stress. Next comes pure shear. So how the pure shear we can denote? Both having the, when both the stresses are non-zero. They should not be non-zero, but they have an equal magnitude but opposite in nature. Now see, in that kind of cases, the Mohr circle will be, the center will be on the origin and both will be have equally shared in the negative and the positive. These are all the stages of stresses in various conditions. Triaxial stress. In triaxial stress, we have all the principal stresses are non-zero. They all will be having some random values. It can be a positive or negative. It can be distinguished by like this as shown in your screen. Our overall description here, the difference between the maximum and the minimum value of principal stress are sigma 1 minus sigma 2, which should be always be positive. From question, calculate the shear force for beam subjected to the loads as shown in figure. Draw the shear force diagram. Here is a diagram displayed in your screen. In this diagram, this is a fixed and this is a roller. When there is a roller, there will be only one vertical force. But in case of fixed, we'll have both vertical as well as a horizontal force. This is an UDL, uniformly distributed load, till the point C, and this is a point load acting here at the point D, vertical load. Let's go for the solution. Here I have resolved the forces here with the distance. Consider this point RA is a vertical, the horizontal RAX. Here at the point V, this a roller was there, so I have resolved the force, that is RBY. Now what I'm going to do is, first I'm going to find the moment at point A. So here I found the moments. Well, starting from here, this is UDL. How I have said how to find the UDL, that is, this is a small w into total length into L by 2. So 10 into 4 into 4 by 2. 4 by 2 comes 2. Now how to find the moment? The clockwise direction is a positive and anti-clockwise direction will be negative. So this plus plus another one what we have here 20 kilonewton. So 20 all are in same convention, so no need to change that, keep it as kilonewton. This is also clockwise direction. So 20 into what is that, 4 plus 4 8 plus 2 10. So 20 into 10 in clockwise direction. Now comes RBY. RBY is acting in an anti-clockwise direction. So minus RBY into what is a perpendicular distance, 8 equals 0. So from here if you simplify this, you get as RBY. Now what you do is, now you do summation of all the vertical forces. So what are all the vertical forces? RAY plus RBY, RAY plus RBY minus 20, and here also minus 10 into 40, 10 into 4, 10 into 4. So you get this here, and you know already, you know the value of RBY, and you substitute here, you get as RAY. You get this one. Now summation of horizontal force. We don't have any horizontal force, so RAX will be 0. So here we complete all the reaction forces. Now I will show you how to find the shear force diagram. So here is the now here this is now what we know, RUN, run, right upper negative. This is what we have. We have a right downwards, right side downwards gives a positive. So what will be there? So I will increase the same amount 20 upwards till the 20. Now in between the D and B we don't have any loading. In between the D and B we don't have any loading. So it will be coming constantly till the point B. See, in the B point what we have a load acting vertically upwards. A load acting vertically upwards. So upward, what we know, U upward is a run. Upward means negative. So we can write that is 20. What is the existing value? Take that value here. Then negative of negative 35. What we get? Minus 15. So the minus means what? From the baseline it will go downwards direction till the magnitude 15. Now in between the B to C, we don't have any magnitude. So we will keep a horizontal line till the point C. Now from the C and A we have a uniformly distributed load. Now again we need to calculate the value. How you're going to calculate? Previous value. Take the previous value minus 15 and calculate this. How you got 40? 10 into what is the distance? Distance is 4. Here the distance is 4. So 10 into 4 you get as plus 40 because these are the acting downwards. Downwards means positive. So what you do is, so you calculate that, you get as 25. Now 25 is a positive value. 25 is a positive value. So from the 15 what you do is you gradually increase to the point 25. Gradually increase to 25. Now again what you do at the point A, you have another load acting vertically upwards. Upward means negative. So we have already previously we have 25, now minus 25 it gets 0. So this from this line it will come to 0 and touch the baseline. Make sure whatever the shear force you draw, the free ends will be 0. I didn't want to make a lot. First question. Match the 4 tensile stress strain curve PQRS with the materials listed in the box. So you can see in the graph PQRS, and other side you can see 4 sets of options: polyester, high purity copper, mild steel, soda lime glass. So and we have 4 sets of options. So first recall the graph between the stress and strain. The first one is a brittle plastic or ultimate point is absent where the fracture leads at the beginning. Then comes a tough and strong plastic where the ultimate point is very negotiable. Then comes a strand hardening and the elastomers. Recalling to additional one, see here the ductile material, which is a green color. You can see where this point has a ultimate point, and after the ultimate point it reaches to an fracture. So this tough and strong plastic can be a copper or an aluminium, and here you see a plastic material of very small elastic region, what it happens. Now come to the question again. Now see the first one, curve P. So it has an ultimate point. So you know ductile material is an example of a mild steel. So P with the 3. So in the option, either it can be a B or C, because we have P3 only in B and C options. Now what you do is, now we have a glass here. So what is that glass? Glass is a brittle material, and where it leads to a fracture immediately after it reaches the limit of proportionality. So R with 4. So both the B and C carries the 4, option R4. Now see, you have to either choose this two. Now copper is a very tough material, and a tough and soft material, which comes in the category of Q, that is Q2. So Q2 here in the option C. So if you don't know about the elastomers or the polyester, how it works, so you can blindly choose option C, which is the right answer, is answer C. A cantilever beam having a rectangular cross section with a width 60, depth 100 mm is made of aluminum alloy. The material mechanical properties are Young's modulus 73 gigapascal and ultimate stress sigma U equals to 480 megapascal. Assuming a factor of safety of 4, the maximum bending moment in kilonewton meter that can be applied on the beam is dash accurate to 1 decimal places. Okay, so let's see the solution. Here are the given data displayed. First, what I have done is, I have converted all the units in the gigapascal in pascal and the sigma value in a pascal value. Now we know the bending moment equation, recalling that you have to memorize the formula, that is m by I equals sigma by y equals to E by R. Now I'm gonna take about the left hand side, where taking that we can get as m equals to sigma I by y. Why have taken that one? Because in the question they have asked to find the maximum bending moment. So from there we can write what is I, b dq by 12, and what is y, d by 2, and sigma, that is sigma u by FOS, because they have given the ultimate stress and the factor of safety value. So from there we are going to substitute all those values in the m formulae. So we get as 2 sigma u b d cube by 12 into d into 4. Now you have to apply all the values, sigma u value, b d q value. Remember the b and d q value are given in mm, so you need to convert in meter, that is into 10 power minus 3. And when you substitute in this formula, and we get as 12,000 Newton meter, and in the question they have asked in 1 decimal places, and the unit should be kilonewton meter, so it is 12.0 kilonewton meter. That's the right answer. A solid shaft of diameter d is under pure torsion of magnitude capital T. The maximum tensile stress experienced at any point on the shaft is 4 options. In this question you have to remember the torsion equation. Then previously we have studied a bending moment. Here we have to remember the torsion equation, that is Tj equals to tau by r equals g theta l. Now in this problem what they have asked, a solid circular shaft. So the polar second moment of area is, the formula is displayed here, that is pi d power 4 by 32. So you have to remember. Now what you're gonna do is, we need to find a tensile stress. So you have to consider this on the left hand side formula. So considering that formula region and recalling that is the tau equals to Td by 2J. How I got this d by 2? Because r can be written as d by 2. So by simplifying I achieve this formula. Now we have already seen for solid shaft the polar second moment of area is pi d power 4 by 3 2. Now in place of j I'm gonna substitute this value and we get as tau equals to 32 Td by 2 pi d power 4. Now here we have d, here we have d power 4 that will get cancelled off, and here the 2 and this will get 16. So finally we get as tau equals to 16t by pi d cube, and which matches with our option D. So our right answer is option D. Then comes, if sigma 1 and sigma 3 are the algebraically largest and the smallest principal stress respectively, the value of maximum shear stress is, recalling this formula, tau max equals to sigma max minus sigma minimum by 2. Here the largest means as sigma max, that is sigma 1, and the minimum or the smallest is sigma 3. So you can substitute in this equation to get a tau max or a maximum shear stress. So we get as tau 1 minus tau 3 by 2. So our right option is option B. Which of the following statements is and are true about the state of body in plane strain condition? All the points in the body undergoes displacement in one plane only. For example, the xy plane leads to epsilon zz, gamma xz equals to gamma yz equal to 0. All the components of the stress perpendicular to the plane of deformation, for example the xy plane of the body, are equal to 0. That is, sigma zz equals tau xz equals to tau yz equal to 0. R1, except the normal component of the other components of the stress perpendicular to the plane of deformation of a body. For example, the xy plane are equal to 0. That is, sigma xx is not equal to 0, but tau xz equal to tau yz will be 0. Now they have given 3 sets of statements, and from there we have to find which statement is correct for plane strain condition. So for that you have to know what is meant by plane strain condition. For the plane strain condition, the strain components perpendicular to the plane of plane strain condition are 0. If the xy plane of the plane strain problem, then as per they have given in the problem, that is where the non-zero terms, that is which all be 0, that is sigma x, sigma y and sigma z and tau xy, and another non-zero strain will be sigma x, sigma y and gamma xy, which you can see the statement P is already correct. The other things, the other components will be 0. See here the R option here, so we can completely ignore that this cannot be true, because the plane, it is not about the plane or deformation. Okay, right? Because see here they have given sigma zz, but already the sigma zz is a non-zero term, it cannot be 0. So we can ignore that Q is a wrong statement. So either it can be option A or D. Now look to the option R or statement R. What they say that sigma z is not 0, but the tau xz and tau xy is 0. See here the sigma z is non-zero term, which matches with the statement. That means where we can choose the option D as a right answer. The state of stress at a point for a body in a plane stress is shown in figure below. If the minimum principal stress is 10 kilopascal and the normal stress sigma y in kilopascal is 4 options. So in this question they have given the form diagram. In the diagram what are things has been given? Sigma x and tau xy, and from this question we have to find sigma y. So what they have asked, minimum principal stress. Before that you have to remember this formula. The first one, sigma y, is a maximum principal stress, and the second one is a minimum principal stress, or denoted by sigma 2. So as per in a given Daters. What is given? Sigma 2 is 10 kilopascal, sigma x equals to 100 kilopascal, and tau xy is 50 kilopascal, and from here we have to find sigma y. So we already know the formula. You have to memorize this formula. It's very easy, but make sure that you don't keep the 2 outside, so that will give you a wrong answer. Please memorize the formula correctly and practice it. So now from this formula we can apply the values. We get as 10 equals to 10 plus sigma y by 2 minus root over 100 minus sigma y by 2 whole square plus 50. Now from here, rearranging that, this term I will keep in the left hand side. So we get at this. From here, by further simplification, we get that minus 80 plus sigma y by 2 equals to minus of root over of that terms. Now from here we need to simplify and find the sigma y value. So from here what we can do, squaring both the terms. After squaring both the terms, the minus terms will get lost and the root over also will get lost. So from here, after further simplification for both the side, we have the sum plus of something square, that is a minus a plus b whole square, and a minus b whole square formula you have to apply. After applying, you will get the sigma y square on both the side. You can cancel off the sigma y from both the side, and you will finally, after simplification, further simplification, we can get the value as sigma y equals to 37.78 kilopascal. So which follows our right answer with the option C. A cantilever beam of length 2 meter with a square section of side length 0.1 meter is loaded vertically at the free end. The vertical displacement at the free end is 5 mm. The beam is made of steel with a Young's modulus of 2 into 10 power 11 Newton per meter square. The maximum bending stress at the fixed end of the cantilever is. So they have given 4 set of questions. Now you know the cantilever beam. Now a point load is acted vertically at the free end. So from here, and what are things has been given? They have given the length of the beam, that is 2 meter, and the width. So here they have given a cross section, square section. So we can say as W equals to 0.1 meter equals to H. Vertical displacement Y is 5 mm. We can write as 5 into 10 power minus 3 meter. Young's modulus given, and from here what we have to find is maximum bending stress. How much acting at the free end. So this is a first you need to identify the problem, and from here you have to use our multiplications of various ideas into it. So first you see I have used a bending moment equation, that is mi equals to sigma y equals to ER. Whenever you see they have given the bending stress, first you recall the bending moment equation. Recall that. Now from here, what are the things you know? Always consider the left hand side, that is m by I equals to sigma by y term. You consider that. From here, and what is given? What is y here? Y is a vertical displacement which is already been given in your problem, that is 5 mm or 5 into 10 power minus 3 meter. So from here you know the L value, you know E value, that is Young's modulus, and you know the I. What is I? Is the second moment of area, which is a rectangular section. The formula is BD cube by 12. You can apply in that formula, and from here you can find the how much vertical load acting on a end of a cantilever beam. So from here we apply, after applying the value we got as W equals to 3125 Newton. Now from here we have already retrieved what is a W value. Now recalling the bending moment, from here what you have to find? Bending stress. So we can write sigma equals to my by I. Now in this problem they have not given how much movement acting on the cantilever beam when a load is acting at the free end, but you know the formula for that. What is movement when at the load? That is movement equals to W into L. So you have to recall that and you have to apply that ideas, that is sigma equals to WLY by I. So here you know the W value, you know L value, we know the Y value and I value. After applications, what is I? BDQ by 12. and you get a sigma value is 375 into 10 power 5 Pascal. From here they have asked in the question in megapascal, so you have to divide 10 power 6 to get as 37.5 megapascal. So right answer is answer B. The minimum axial compressive load P requires to an initial buckling for an pin-pin slender column with a bending stiffness EI and the length L is. We have four sets of questions, four sets of option. Before that, you have to recall four end conditions of an column. You had this displayed here, but in this question what they have specified, both the ends are pinned, so you have to focus on both the ends are pinned, and you have to recall the Euler's formula, that is critical load for Euler's formula, it is P equals to pi square EI by LE square. What is LE? Is a effective length. So in case of both the ends are pinned, what is the formula for effective length? That is L equals to L. If you want to have an idea more depth about the column, the link in the description below, you can go and check.
Today our topic is column. That is, what do you mean by column? Column is a vertical structure through compression. So compression is a very important word when it comes of column. Members in column are compression members. You remember this C and here also C. Both are compressive members. Now look into few of the columns. These are the vertical patterns. The vertical structure which going through this compression are the columns. These are the types of columns. These are the all are the types of columns. Column has four end conditions. The first one is, remember, both ends are fixed. When both ends are fixed, that means like this. Then second one is fixed and hinge. So one end will be fixed, another end will be hinged. This is a symbol of hinged. The next one is both are hinged. That means it will be this is a diagram for both the ends are hinged. Next one is a one end is fixed and another end is free. One end is fixed and one other end is kept free. So in this kind of fixed and hinged, what happened? In this, a compressive load will be acting on it. But in case of fixed and free, only one compressive load will be acting from one side. This is fixed and hinged. What happens when there is a fix? This goes some amount distance from here, and when it's hinged, it directly starts from the starting point. L equals to L by root over 2. Now the third case is both the hinge. When there is a compressive load from both the side, what will happen? It will be same. And the last one is one end is fixed, another end is kept free. So when there is a compressive load, so it will be coming like this. So L is equal to twice of L. So now these are the, now you see this four end conditions. So you remember the formula, it is Euler's formula, P equals to pi square E I by LE square. This is a general formula. Now this is the first case. What is the first case? Is both the ends are fixed. So when there is a fixed, some amount of deflection it goes along with the length, and then get some deflection along the x-axis. So how we can find the effective length? Effective length becomes that L by 2, that is half of the length of the member. Now what is it? This is a length. This is a length. So how we can find the effective? That becomes a half of it. So half it is going along with it and the remaining one gets half. Okay. Now next comes the one end is fixed and another end is hinged. So when this is a complicated one, it's a mixture of the fixed and hinged. So what we get is L equals to L by root over 2. Next comes the one end, both the ends are hinged. So when both the ends are hinged, when we say hinged, it directly follows from the point. The elongation from the point. So the effective length is L equals to L. Next come the free, one end fixed, one end free. So L equals to twice of L. The length gets twice because the curvature, if you see, if go along with it, it gets double of the original one. So how you can memorize these terms? So first you remember sequence wise. The first one is a both ends are fixed. Then comes the complicated one, fixed and hinged. Then the both ends are hinged. And the last one is a fixed and free. So okay, how it comes? It first comes L by 2, then L by root 2, then L, then comes 2L. Now how you can know the formula for this particular pressure, this force? Now P, you know the general formula. In place of general formula, you place this LE over there. So pi square EI. What is LE over here? That is L by 2. L by 2 whole square. If you put whole square, this 2 square 4. That means you will get as P equals to 4 pi square EI by L square. This is a formula for when both the ends are fixed. Similarly, if you apply this value in this formula, you will get as P equals to 2 pi square EI by L square. Now you are gonna substitute this value in this formula, general equation. Then P equals to pi square EI by L square, because here LE and L are same. So you will just convert this LE square. Now this one, P equals to, substitute there, P square EI by here 2L. 2L means 4L square. You will get 4L square. Now here you see this. Which one will create the maximum critical load? This one. This is the condition where you will create a maximum critical load. See the formula among all. This one will be, if keeping the E, I and L constant. So here we have 4 behind. So this one will be creating a high or maximum critical load. And which one will be creating the least value? See, the denominator we have 4. So this condition, what is this condition? That is one end is fixed, another end is free. So this condition will put the least case. This is a list and there is a maximum. What is this maximum? When one end is a free, both the ends are fixed. When both the ends are fixed. So both the ends are fixed will create the maximum value, and one end is fixed, another end is free, will create that least value.